Okay, so we are talking about fixed universe successor problem. Just to recap, we have a so the goal is to maintain a dynamic set S, which is of n element. The size of S is n say, and S is coming from a fixed universe, which is basically having u elements. So it is starting from u to 1. So this is to so that we can able to perform this operation, we should able to insert an element x which is not in S. So this is the insertion, and we should able to delete an element from S, and we should able to find the successor. So we should able to get the next element after S in S. Okay. Now, so this operation we should able to perform, and these two operations makes this set S dynamic, and this is the successor query. Similar, we have a predecessor query. So suppose S is suppose U is 16. So our universe is, so this is fixed universe. That means we know the elements of S. We have seen the many dynamic set data structure to handle the dynamic set, but here the set is some specific elements are fixed. We know the elements, where from they are coming. Elements are coming from this universe. Okay, we know the universe, and then we have to do these operations. These two are dynamic operation, and this is a query operation, successor query. Okay, so now this operation. Now suppose S, this is U, and suppose S is say 1, 9, 14. Say 10, 15, say at some point of time. Okay. Now the successor of 1 is what? Successor of 1 is basically 9, and the successor of 2 is also 9. So successor of x means the next element which is in S after this 2, and this x need not be in S. This x is coming from, so successor of x is coming from the universe. So we can query the successor for any element from the universe, need not be in S. It may be in S, for example this one, but may not be in S, for example this one. Okay. So this problem we want to we have seen some data structure in the last class, but this problem we want to solve in log u time, the successor query or insert. So and we have seen in the last class, to get log u we have to have this type of recurrence. Okay, so this type of recurrence. So we have to achieve this type of recurrence, then we can have the solution. So this solution is log of log u. So the idea is from Peter van Emde-Boas. This is the person who developed this data structure. So let us start with the starting point is a array. So this is a bit vector. This we have already started in the previous lecture. Just to recap, so we start with this is the starting point, bit vector. So what we are doing, we are having a U array of size small u. Okay, so we just have, and suppose our S is say 1, 9, 10, 15. So we have 1, here 1. So say here 9 and 10, say dot. So 1, 1. Rest start 0. So this is just a bit vector. So light of light call. So this array will be, so u of x. So u of x will be 0 if x in is S, sorry 1 if it's, so switch on, otherwise switch off like this. Okay, that room is empty. So and we have seen the insertion and deletion will take, which the insertion and deletion will take the constant time, because if we want to insert 3, so we go to u3 and we put it 1. If you want to delete 9, so we go to u9 and we put it 0. So, insertion and deletion both will take the constant time, but the problem is with the successor. Now, what is the successor query? Suppose our array is like this. So, all are 0 except the last one and few beginning one. Now, suppose we want to have a successor query on 2 or 3. So, it has to scan the whole array. So, successor query will take order of u. So, successor will take order of u, but we want to achieve this by log u. So, for that we want to break it into square root of u. So, how we can break this array into square root of u array? So, that is the step 2. So, that is the second step. So, we just, so this is the array of size u. So, this is step 2. So, this is our u array. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So, our u is here, our u is 16 say. So, we have a array. So, how we can break it into square root of u? Square root of u is 4. So, what we do? We just break it into 4 size blocks, or this is called also widgets or blocks. Okay, this is the first block or 0th block, 1, 2, 3, 4. This is the next block, which is the 1th block, 1, 2, 3, 4. This is the next block, this is the next block, like this. So, this is our, this is the first block, this is W0 we denoted by this, then W1, W2, and then W3. Okay. And this is, so how many blocks are there? How many blocks are there? So, there are root over of u blocks. Here u is 16. So, root over of u is 4. So, there are 4 blocks. And what is the size of each block? Size of each block is also root over of u. So, it starts from, so each block, so Wi is basically in general. So, it is basically 0, 1, 2 up to root over of u minus 1. Okay, 0, 1, 2 up to root over of u minus 1. This is the ith block. So, here u is 4. So, for the simplicity, this is the situation. Okay. So, we break it into, so basically the idea is this was one dimensional array. So, we are visualizing as, so we are breaking into 2 dimensional array. So, this is basically, so this is again start from 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Okay, just a 2 dimensional array in C, we can say. So, this is basically W0, this is basically W00 like this. So, so this is basically W00, W01, W0, W02, W03. Okay, just 2 dimensional array. So, we just break the 1 dimensional array into 2 dimensional array. Okay, so now, so our S is basically, suppose our S is 1, 9, 10, 15. So, this is basically 1 and 9 is basically what? 9 is basically, this is 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, and this is 15, and remaining are 0. Okay. So, this is our data structure. Okay. So, now how to use this data structure for our operation like insert, delete. So, suppose we want to insert a x. So, we want to insert x. So, what we do? We just convert x into binary and we write x into two parts. So, we just convert x into binary and it will be of size root u, and we take this part is high of x and this part is low of x. Okay. So, basically x is high of x into root u plus low of x. So, this is the square root of u bits and this is the square root of u bits. So, we convert x into binary representation and of u size, and we take the first root u bit as a high of x and the next root u bit as a low of x. For example, if we take say x equal to 9, okay, suppose x equal to 9. So, for 9 how we can convert? So, this is of u is 16. So, square root of u is basically 4. So, 9 how we convert into 9 into binary? 9 is basically 1 0 0 1. So, this is 8 plus 1 9. So, this is 9. Now, this is basically our high of x and this is basically our low of x. Okay. So, this we are so this is basically, so this is not square root. So, this is basically yeah. So, the first half the lower half is called low of x, upper half is called high of x. So, this is basically high of x, this is basically low of x, and this high of x will give the block number. So, this is, so what is h? H is 2 and this is basically 1. So, this is basically our position of 9 in this 2-dimensional array. So, because this is basically give us h of x will basically give us is the block number, widget number. So, basically w of h of x. So, here h is 2. So, basically w2. So, w2 is basically this block. Okay. So, in w2 we have to see the, in that block this basically gives us the position of x. So, this is 1. So, basically we need to look at this 0 1. So, this position is basically w2 1. So, this is basically w of, so w of h of x and low of x. So, this is basically gives the position of x in this 2-dimensional representation. So, this is a nice data structure. This is just a 2-dimensional array. So, this will give us the position. So, to insert x, what we need to do? So, to insert x, we will do just, suppose we to insert x, we will go to, so we break it into, so x into two parts, high of x and low of x. Okay. So, we basically convert x into binary, then we take the first half most significant bits h and least significant bits l. So, what we do? We go for w of h of x, then we go for low of x and then we put it 1, that is it. And similarly delete also, if you want to delete an element, delete an x. So, we just go to that position of x in the 2-dimensional array and we put it 0. Okay. So, suppose we want to insert say 5. So, suppose x equal to 5, we want to insert 5 say. So, here x equal to 5. So, what is the binary representation of 5? So, this is 0 1 0 1, this is 5. So, this is high of x, this is low of x. Okay, so this is basically high of x, which is basically give us what? This is 1, and low of x, this is also 1. So, we have to just go for W of 1 1. So, W of 1 is this, 1 is this. So, this is basically make it into 1. So, this is the position for x equal to 5. So, we just put it 1. Similarly, if we want to delete 9, so we have to convert into this high of x, low of x, we go to that position 9. Now, how much will take the successor query? So, the how to do the successor query? Suppose successor of x. Okay. So, suppose x is like this, s is say 1, 9, 10, 15 say. Suppose we want to find the successor of say 2. What to do? So, we just convert suppose x equal to 2. We want to find the successor of 2. So, what we do? We convert 2 into this low of x, high of x. So, 0 0, 1 0. So, this is low of x, this is denoted by visit block number, and this is basically, so this is 0 and this is 2. So, basically we need to find the successor after this. So, what we do? We first find the successor in this, and then we find the successor in this. We find the non-empty bit in this after this, and then we find the non-empty bit in this. Then we find the non-empty bit in this like this. So, to find the non-empty bit in this, it will take order of u time, because size is order of u. Again, this we may not get the successor here. So, we may have to find the non-empty successor here like this. Okay. So, then maybe here also we need to look at like this, or maybe we can get at the end. So, this way it will take order of root u into root u. So, order of u. So, no gain. But can you think of some augmentation of this data set? Because we know this block is 0 block. There is no 1 in this block. So, to search in this block is wastage of time. So, how to avoid that? Can you think of some augmentation in this data structure so that we can avoid to search in this block? Because we know there is no 1 in this block. So, if we can have this knowledge beforehand, so if we can do some augmentation in the data structure, so that we will avoid search in that block. So, to do that, we will do some augmentation of the data structure. So, we will do that just the non-empty block. I mean, we just put a single bit information. This is the augmentation of the of this data structure. We can put a single bit of information. This will denote as say summary bit, sum, or this is denoting as the non-empty bit. Whether this block is empty or this in this block there is somebody is there. So, to denote this, what we do? We just or we can say this is the non-empty. So, for this block there is 1. So, this is 1, this block it is 0, nobody is there, this block it is 1, this block it is 1. Now, what we do? Suppose we want to find the, so this will help us. How? Now, suppose you want to find the successor of 2. So, we first find the successor in that block where 2 belonging. So, this is this block. So, after this we find the successor. If we are getting okay, otherwise we will next look at the non-empty block. Okay, we know that there is, so this block is empty. So, there is no question of looking at this block for 1. So, we just go for the next non-empty block. So, we know, so we go for this block, and then we find we search for a successor in this block. So, that is the idea. So, let us write that code. So, this is basically the idea. So, let us write the code. This is the So, basically we are finding the successor of x. So, what we do, we convert x into high of x and low of x. Okay. So, we look at the successor of x within the widget or block w of high of x after starting after low of x. Okay. So, basically we have these blocks. We have these blocks and we have this summary bits or non-empty bit. So, this is our w. So, suppose this is the w of h of x. This is the block where this x belonging, and suppose this is the low of x, position of x. Now, we find the successor after this in this block. Okay. And if we are not getting, then what we do? We will find the next non-empty block. Okay. So, if successor found, we return otherwise else we find the next non-empty block. Suppose else find the next non-empty we get, and suppose that is wi. Suppose next non-empty we get is say wi, and then we know this in this wi there is 1. We do not know where it is, but we know there is 1. So, then what we look at? So, we have to look at 1, then we find the successor of what? Find the successor of, say we start from the beginning, find the successor of say minus infinity or minus 1, minus 2, because it is starting from 0, 1, 2. So, basically we are looking for first one here. So, basically we find the successor of say minus infinity or minus 1. So, find the successor in wi starting from beginning. Basically, we are looking for first one in that block starting from say minus 1 or minus infinity like this. Okay. So, this is the code. Now, what is the time complexity? Now, this will take square root of u time, and if we and then if found, then okay, otherwise we have to find the next non-empty widget which is having 1. So, that is also sort of finding successor query. So, this also will take order of u, this is order of u, and this will also take order of u. So, this total time is basically time complexity for this algorithm is order of square root of u. So, sorry, this is square root of u. Okay. So, this is the time complexity, but we want to do it log u. So, for doing that we need to get a recurrence relations. So, how this algorithm can be think for a recursive call. Okay. So, for that, can you think these steps are in a recursive call? Okay. So, this is a successor call, say so this is a successor call, say successor in w. So, w is a successor of x in 2-dimensional array say. Now this is can you think this call is a, so this is also a successor call. So this is a successor of what? Successor of L of x in W of H of x. So this is a successor call after L of x. So this is a successor call, successor of low of x in that block. Okay, and if found okay, otherwise this is also successor call. This is basically J, which is giving us successor of what? Successor of, so basically what we are doing here, we are looking at the, so these are our blocks. So these are our blocks and these are our non-empty bits. Okay. So this first we are looking at that W of, say suppose this is x is belonging here. So this is basically W of H of x block, and this is basically say position of L of x. So we are looking at the successor here. If found okay, otherwise then we are looking at the this non-empty array. So we are looking at the successor in this non-empty array after this H of x. So this is this call. So this is basically I is basically successor of what? After W of x in this non-empty array. So this is the successor call, because we are looking at, so here some one, some zeros like this. So we are looking for the next one in this array. So this is an array of size W of u. So this is an array of size W of square root of u. So 0, 1 up to square root of u minus 1. Okay, so we are looking at the successor after H of x. So this position is H of x. We are looking at the successor, that means next one. So this is also successor call. So we are looking at the next one after this H of x. So this is basically 1. So this is a successor call. And then we have here finally we have a last successor call. So this is 1. So this is the ith block. So this is basically Wi. So here we know there is a 1, but we don't know where it is. So we have to look at that 1. So that is also successor call, successor of minus something, because so that is basically also successor of the last one, say minus infinity of W of I. So this is also successor call. So how many successor call? If we, so in the worst case we are not getting here, then we have to go for this call and this call. So 3 successor call, but we want to have only 2 successor call. So how we can get it in 2 successor call? So we have 3 successor call. That means our recurrence is, for this algorithm, our recurrence is this is our recurrence, but we want only 1 successor call. So how we can achieve only 1 successor call? So we need to do, that is the idea of Venn MDev was, we need to do some augmentation, more augmentation in the data structure. So how we can do? So suppose this is the case. Okay, so this is the non-empty bit or the summary bits. So now suppose, so now either, so we are looking for the first successor call is basically successor of L of x in W of H of x. Okay. So if we get it, then okay, just 1 call. Otherwise, we have to go for 2 more calls. So how to avoid this? So, we can do one thing. So, how to avoid this call? So, to avoid this call, we can just put the maximum. This is another augmenting of the data structure. So, we put a max array. So, what is this max array is telling? Max array is telling we store the maximum index up to where this 1 is. So, suppose it is like this, say 1 0. So, this is 0 1 2 3. So, this maximum will be 2, because we know up to 2 there is 1. So, after 2 there is no 1. So, that is the another augmentation of the data structure. So, like this. So, if you do this, then this successor query is not required, because we just first check, yeah, this required if max is greater than low of x. Then we know there is a 1 after low of x. Then there is a meaning of this successor call. Otherwise, we will not go for this successor call. So, this way we save one successor call, because in the worst case, suppose it is not there. Suppose max is less than low of x. Then what we do? We will not do this successor call. Then we have to look at this non-empty bit. So, that successor call is mandatory. So, successor of h of x into the non-empty array. So, this successor call is must, it is mandatory. It will look at the non-empty bit over here. So, 0 1 says 0 1 like this. So, this was 9. Okay. So, this successor call is mandatory, one successor is called mandatory. Now, next we are doing another successor call, like in this set. So, this is I set. So, this is Wi. So, so successor of say minus infinity Wi. Now, can you think of some more augmentation so that we can save this successor call? Yes, we can store the minimum. Over here. So, where is the index? Where is the minimum? So, that is basically, so this is basically 0 1. So, this is 1, because minimum is storing what? So, this will save this successor call. We do not need this successor call. By checking the minimum value, so this will give us the answer. So, this is the just a one call. So, we have to take this call to find the non-empty bit. Either we find here if the max is greater than low of x, then we know there is a 1 which is after low of x. So, we will do the successor call there, then we got the value successor. Otherwise, we have to look at this, otherwise we will just do not call this successor call for this. So, we are saving one successor call, but we have to do this successor call to get the non-empty bit, non-empty block. So, suppose this is the non-empty block. Now, earlier we are doing a successor call, say minus infinity in that, but this is not required if we do the further augmenting by storing the minimum, where the minimum index is. So, this is the 1. So, this is 0 1 2 3. So, first one is here. So, this index we store and this index will be the output. So, no need to do the successor call. So, this is a one successor call. So, we reduce 3 successor calls to one successor call by doing this augmentation. But here we have to be careful, here we are storing the index, it is not just the 0 1 vector. So, this should able to store the index. So, these are the integer array. Okay, so this is the good news. So, this is our recurrence, and the solution of this recurrence is log u. So, this is the idea of Van Emde-Boas. So, this is the basically the data structure augmentation on the basic the bit vector array. Thank you.